Welcome to Learn with us. This is the seventh lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about current equation of diode, and we also started another topic in our last lecture, which is modeling of diode in forward characteristics. In this topic, we first understood exponential diode model. You studied that in this exponential diode model, there are two alternative ways for obtaining values of unknown quantities, that is diode voltage and diode current. First way is graphical analysis and second way is iterative analysis. What are the learning objectives of this lecture? In this lecture, you will understand other diode models that are used for modeling diodes in forward characteristics. These models include piecewise linear model, constant voltage drop model, ideal diode model, and small signal diode model. Now we will understand piecewise linear model. It is also known as battery plus resistance model. This model is more accurate model from ideal diode assumption. This method is used to approximate the diode characteristic curve as a series of linear segments. That is, it approximates exponential curve of diode by a straight line. In this model, the real diode is modeled as three components that are connected in series. Now, look at this. This is real diode model. Now, in piecewise linear model, this diode is replaced with an ideal diode, a voltage source, and a resistor, and all these three components are connected in series. So this is your real diode model, and this is piecewise linear model. Now we will understand current equation of diode in piecewise linear model. We know that the equation of diode current is ID is equal to Is e raised to the power v divided by nVt, and this equation is representing exponential characteristic of diode. Now, how we are going to find diode current equation in case of piecewise linear model? Look at this model. Here we will apply KVL to obtain our equation of diode current. So how you are going to apply KVL? First we'll put positive and negative signs on this voltage source and resistor. Now we will write our KVL equation. We'll start from here. So it will be something like minus VD plus VD naught plus ID RD. We know that V is equal to IR. Okay, so here we will write this like this. Now we can also write this equation as VD is equal to VD naught plus ID RD, or VD minus VD naught is equal to ID RD. So what will be the equation of diode current? It will be ID is equal to VD minus VD naught divided by RD. So this is your equation of diode current for piecewise linear model. Now we will understand current voltage characteristic curve of piecewise linear model. For this we will plot the relationship of both diode current equations that we have studied in our previous slide on the IV plane. Now look at this. This is the IV plane where the variable of x-axis is Vd or diode voltage and the variable of y-axis is Id or diode current. Now we know that the first diode current equation is Id is equal to Is e raised to the power v divided by nVt. Now look at this. Here this curve is representing this exponential diode equation. Now the second diode current equation is Id is equal to Vd minus Vd naught divided by Rd. If we break this equation, it will become Id is equal to Vd divided by Rd minus Vd naught divided by Rd. We know that the formula of slope is y is equal to mx plus c, where this y is y-axis variable, this x is x-axis variable, and this m is a slope. So if we compare these two equations, we can write it like this: y is equal to id, x is equal to vd, and m is equal to 1 upon rt, which is. So how you are going to draw this relationship on this IV plane? It is drawn something like this. This is first straight line A and this is second straight line B. Because I have mentioned earlier that this piecewise linear model is used for the approximation of the exponential curve by the straight line. So this is your exponential curve and it is being approximated by these two straight lines in this piecewise linear model. Now, if you look at line A, here ID is equal to 0 and it shows that the diode is off. Okay, now if we look at line B, it is slope which is 1 upon Rd and the direction of this slope is upward from left to right because its value is positive. Now here this point is Vd naught, which is the intercept of line B on voltage axis or x-axis. Now here we know that this line is straight. It means it has no constant. So if we compare these two equations, here C is minus Vd naught divided by Rd, which is 0. Okay, so this is the current voltage characteristic of piecewise linear model. Now, look at this example. If you have to determine the diode current ID and the diode voltage Vd for the circuit where VDD is 5 volts, R is 1 kilo ohms, Vd naught is 0.65 volts and Rd is 20 ohms. Now if you have a real diode model which looks like this, where this is resistor, this is VDD and this is your real diode. Now what will be its equivalent piecewise linear model? It will be something like this, where this real diode is replaced by an ideal diode, a voltage source, and a resistor that are connected in series. So this is R, this is VDD, this is VD, this is VD naught, and this is RD. Okay, so how we will start our analysis? First, we will obtain our KVL equation. For this, we will put positive and negative signs. Okay, now we'll start our analysis from this point. So our KVL equation will be minus VDD plus, okay, here the current is flowing in this direction, which is ID. So here we'll write ID R plus VD plus VD naught plus ID RT is equal to 0. Okay, now if this ideal diode is forward biased, it means in this case VD is equal to 0 and ID is maximum. So now this equation A will become minus VDD plus IDR plus VD naught plus ID RD is equal to 0. Now we will put our given values in this equation. So we'll write minus 5 plus ID 1000 plus 0.65 plus ID 20 is equal to 0, or by solving this equation we will get ID is equal to 4.35 divided by 1020 is equal to 4.26 milliampere. Okay, so this is the value of diode current. Now, if this ideal diode is reverse biased, it means VD is maximum and ID is 0. So now how you are going to write this equation A in this case? It will become something like minus VD plus VD plus VD naught is equal to 0. And if we rearrange this equation, it will become VD is equal to VDD minus VD naught. If we put our given values, it will be 5 minus 0.65 is equal to 4.35 volts. So this is the value of diode voltage. Okay, so this is how you are going to analyze any circuit using piecewise linear model. Now we will look at constant voltage drop model. This model is the simplest and most widely used diode model. It assumes that a forward conducting diode has a constant voltage drop value of 0.7 volts without any incremental resistance. This model is the one most frequently employed model in the initial stages of analysis and design. Now, in this model, there are two components that are connected in series. Now, look at this model. This is real diode model. Now, in constant voltage drop model, this real diode is replaced with an ideal diode and a voltage source having a constant voltage drop of 0.7 volts, and these two components are connected in series, as you can see here. Now we will understand current voltage characteristic curve of constant voltage drop model. Look at this IV plane where the variable of x-axis is VD or diode voltage and the variable of y-axis is ID or diode current. Now look at this curve. Here this curve is representing this exponential diode current equation, which is IT is equal to Is e raised to the power v divided by nVt. Now in constant voltage drop model, vertical straight line is used to approximate this exponential curve. So it is drawn something like this is line A and this is line B. And as I have mentioned earlier that this model has a constant voltage drop value of 0.7 volts. So this is 0.7 volts. Okay, here this line B is approximating this exponential curve. Now look at line A. Here ID is equal to 0. It means diode is off. Now if we look at line B, it is parallel to y-axis. It means its slope is undefined. So this is current voltage characteristic of constant voltage drop model. Now look at this example. If you have to determine the diode current ID and the diode voltage VD for the circuit where VDD is 5 volts and R is 1 kilo ohms. So how you are going to analyze this circuit using constant voltage drop model? For suppose this is your real diode model where this is VDD, this is R and this is diode, that is real diode. Now what will be its equivalent constant voltage drop model? It will be something like this, where this real diode is replaced by an ideal diode and a voltage source. This is VDD, this is R, this is VD, and this is a voltage source which has a constant voltage drop value of 0.7 volts. Here the current IT is flowing in this direction. Okay, so how you are going to analyze this circuit? First you will write KVL equation. This is positive, this is negative, this is positive, negative, positive, negative. So we'll start our analysis from here. So our KVL equation will be minus VDD plus IDR plus VD plus VS is equal to 0. Okay. If this ideal diode is forward biased, it means VD is equal to 0 and ID is maximum. So this equation A will become minus VDD plus IDR plus VS is equal to 0, and after putting our given values it will be minus 5 plus ID 1000 plus 0.7 is equal to 0. ID is equal to 5 minus 0.7 divided by 1000 is equal to 4.3 milliampere. So this is the value of diode current. Now what will be the value of diode voltage VD? We know that this constant voltage drop model has a constant value of voltage drop which is 0.7 volts. So this is the value of diode voltage in this model. Now what is an ideal diode model? In applications that involve voltages much greater than the diode voltage drop, which is in this range, in this case we may neglect the diode voltage drop altogether while calculating the diode current. So the result is the ideal diode model. In this ideal diode model, VD is 0. This model provides very quick analysis for gross estimate. Now look at this. This is an ideal diode. Now what is the IV characteristic curve of this ideal diode model? We have already studied about this relationship in our previous lectures. Here the x-axis is VD and the y-axis is ID. So a straight line on this y-axis is representing this ideal diode model. This is line A where VD is equal to 0. Since this line A is on y-axis, so its slope is undefined. So this is the current voltage characteristic of an ideal diode model. Now look at this example. If you have to determine the diode current ID and the diode voltage VD for the circuit where VDD is 5 volts and R is 1 kilo ohms, so how you are going to analyze? For suppose this is your ideal diode model. This is VDD, this is R, this is an ideal diode, and this is the direction of current ID. So how you are going to start your analysis? First, you will apply KVL. And what will be the equation of KVL here? We'll start from this point. It will be minus VDD plus IDR plus VD is equal to 0. Now, if this ideal diode is forward biased, it means VD is equal to 0 and ID is max. So now this equation will become minus VDD plus IDR equal to 0. So ID is equal to VDD upon R is equal to 5 divided by 5 milliamperes. Now what will be the value of diode voltage VD? We know that in case of an ideal diode voltage, the value of diode voltage is 0. So this is how you are going to analyze any circuit using an ideal diode model. Now here is your class task. If you have a real diode circuit like this, where this is VDD, this is R, and this is real diode, then determine the diode current ID and the diode voltage VD for this circuit with VDD is equal to 5 volt and R is 10 kilo ohms. First you have to use piecewise linear model when VD naught is 0.7 volts, and then you have to use constant voltage drop model with VD is equal to 0.7 volts. Take 8 minutes to complete this task. Now we will understand small signal diode model. This model is operated at a DC biased point on the forward current voltage characteristic curve. In this model, a small AC signal is superimposed on DC. This model is linearization of exponential model. Now, this is simple diode model where this is VDD, This is R. Current ID is flowing in this direction. This is diode and diode voltage is VD. Now consider a situation in which this VDD is undergoing a small change delta VDD. This diode voltage is changing by an increment delta VD. Similarly, this diode current is changing by an increment delta ID. So for this situation, circuit becomes like this, where this is representing change in VDD. This is VDD. This is R. Now current is ID plus delta ID and voltage is VD plus delta VD. So this circuit is representing small change in quantities like VDD, ID and VD. Now we will understand the current voltage characteristic curve of small signal diode model. This is the IV plane where the variable of x-axis is VD and the variable of y-axis is ID. Now here this curve is representing exponential diode current equation. From constant voltage drop model, we know that this exponential curve is approximated by a straight line, which is a slope that is 1 upon RT. Now, this straight line or slope, it is tangent at Q. This Q is a bias point. The coordinates of this bias point give us the values of unknown quantities like diode current and diode voltage. It means if we draw a straight line from this point on y-axis, we get the value of ID, which is bias current. And if we draw a line from this point on x-axis, we get the value of VD, which is bias voltage. Now, as I have mentioned that in this small signal diode model, a small AC signal is superimposed on DC. So we draw this AC signal like this. This is showing current ID, and for voltage, this small AC signal is drawn like this. This is VD. So this is the current voltage characteristic curve of small signal diode model. In case of small signal diode model, there are two quantities. One is a DC quantity and other is time varying or AC quantity. Okay. Now in this case, we express the voltage across the diode as the sum of DC voltage and time varying voltage, which is equal to VD. Correspondingly, the diode current will be ID plus ID is equal to ID. Now here these terms are representing DC quantities. Note that they are written in uppercase with uppercase subscript, and here these terms are representing AC or time varying quantities, and they are written in lowercase with lowercase subscript. Now, these are total instantaneous quantities that are written in lowercase with uppercase subscript. We know that instantaneous quantities are those that are measured at a particular instant, and they are DC plus time varying. We know that IT is equal to Is e raised to the power v divided by nVt. In case of diode, this n is 1 and this v is equal to Vd. So this equation now becomes Id is equal to Is e Vd divided by Vt. Now for instantaneous current Id, this formula will become something like this, because we know that instantaneous quantity is the sum of DC and time varying quantity. Now if we split this exponential term, we'll get this equation. Now look at this term and compare it with this equation. As you can see, this term is equal to Id. So after substituting this value here, we get this equation. Now, from power series expansion formula, we know that Ex is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus so on. Now for smaller values, this formula is reduced to Ex is equal to 1 plus x. Now, if the amplitude of this signal Vd is kept sufficiently small such that Vd divided by Vt is less than 1, and if we apply this power expansion formula here, then we'll get Id is equal to Id multiplied by 1 plus Vd divided by Vt. Because if we look at this exponential term, here x is Vd divided by Vt. Okay, so what is this equation? This equation is the approximate expression, which is also called small signal approximation, and it is valid for amplitudes that are smaller than 5 millivolts. Now we can write this equal to sign like this, which is showing approximation. Now we just derived that instantaneous current is equal to Id 1 plus Vd divided by Vt. If we open this bracket, we get ID is equal to V plus ID VD divided by VT. We know that this instantaneous current is the sum of DC current plus time varying current. So if we substitute this value of instantaneous current in this equation, we'll get an equation like this. Now this ID is going to cancel this ID, so this time varying current will be equal to DC current VD divided by VT. Now what is this equation called? It is called diode small signal conductance. Now from Ohm's law, we know that V is equal to IR. Therefore, R will be equal to V upon I. So if we rearrange this equation like VT divided by ID is equal to VD divided by ID. Now here this term is equal to RD. So can be written as RD is equal to VT upon ID. Now this equation is called diode small signal resistance or incremental resistance. That's all for today. What are the key takeaways of this lecture? In this lecture, you studied about piecewise linear model. You also understood constant voltage drop model. In this lecture, you also studied what is an ideal diode model and what is a small signal diode model.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.